technically you asked me to put on the mic. So
Yeah, I'm not talking now, just I'm drawing. Okay, so during the break there was a question whether the MR of the polycrystalline films, how close they can come towards MS, okay, in polycrystalline films. So, I have seen this growth, I mean the improvement in making MR as close to MS in possible. This has happened in magnetic recording technology. So, initially the magnetic recording technology was based on magnetization parallel to the disc surface. So, that is called longitudinal magnetic recording technology. So, in the early days we are using small grains to store information. So, whenever I show one arrow, basically that arrow is the magnetization direction of one particular grain. So, it may be like this or in any other angle, but it is basically one grain. So, we store information in many small grains. Okay, so, if you look at the technology of longitudinal magnetic recording in the 1990s, for example, we can view the EZ direction in two different perspectives for the longitudinal sample. Okay. For example, let us say let us say you are storing in magnetization along this direction parallel to this surface. You can view the easy direction from this angle. Okay, you are viewing the easy direction from this angle, or you are viewing the easy direction from this angle. Okay. So, I am showing the two perspective. So, in longitudinal magnetic recording, your grains may have easy direction. I mean, if you view from this perspective, it may be completely parallel to this plane, or it may be tilted at some angle with respect to this plane. So, magnetization can be this way or like this, okay. A few possibilities exist. And now, if you view from the top, so within the plane, again the magnetization can point towards you, or point towards this wall, or point towards this wall. So, it can point towards many directions, right. So, from the top also you have randomness. So, when you have such randomness, usually the MR is very low compared to MS. So, you may get something like 0.6 times MS. Okay, so, this value is 60% of the MS value. So, people have improved this randomness by using some growing some underlayer and things like that. So, for example, they can minimize the randomness of the easy axis away from the parallel direction. So, you see the randomness is more here, is reduced. So, more easy direction is parallel to the disk surface, but still within this plane there is randomness. Okay. So, in this case you can see the MR approaches around 0.7 times MS. Now, let us go further. You make all these grains to have easy direction parallel to the disk surface, and again this also you minimize. So, instead of this magnetization pointing different direction, I try to force most of the easy direction along this. Okay. So, when I do that, I can go to around 0.8 times MS. That means, this value is 80% of the MS. Okay. So, this kind of improvement can happen. Then somewhere in 2006, our disk industry switched to perpendicular recording technology. Now, the magnetization is not in the plane, now magnetization is perpendicular to the plane. So, when you have perpendicular to the plane, I mean in this direction you do not have much variation, like you see right here within the plane I can have random orientation, but when you orient all the magnetization along the perpendicular direction, there is no in plane variation. So, now you have only variation in the easy direction with respect to the film normal. So, some grains may have easy direction perfectly perpendicular, some may have easy axis tilted along this direction or this direction. So, when you go from longitudinal to perpendicular, you can roughly achieve 90% of saturation magnetization. And now, if you try to minimize this randomness, you try to make all the grains having easy axis perpendicular, then you can bring the MR very close to the MS. So, even with polycrystalline materials, you can improve the process to ensure that your film is textured. So, we call this textured. You try to make all the easy axis along the same direction, then you can achieve high values of MR over MS. Okay, so far we have answered the first two questions. The next question is like For example, yesterday we were discussing about Curie temperature. I asked you a question, if you heat a magnetic material above Curie temperature, then you bring it back to room temperature, whether the ferromagnetic material will be same as ferromagnetic material. You all answered yes, and that is correct. So, my next question was like, in your school you would have learned that if you have a permanent magnet, do not heat it. If you heat it, your permanent magnet will lose its property, right. It is ferromagnetic material, but it loses the north south poles. Okay. So, a permanent magnet has a fixed north and south pole, but if you heat it and cool down, it will lose its north and south poles. It will not attract any magnetic material. So, what happens? What is the reason? And that is what we are going to learn now. And also we are, okay, let us say I have neodymium iron boron in my lab. Say I do some mixing and do all the processes to make it a neodymium iron boron magnet. Okay. So, I did all the chemical steps necessary to make this compound. Okay. I have made this compound, and this compound is in this shape, for example. Okay. But when I do this, this is not a magnet on its own. Okay. So, this piece of neodymium iron boron does not have a fixed north pole or south pole. So, I need to do one additional step to make this a permanent magnet. Okay. So, what I need to do is, I need to subject this particular piece of magnet to a very strong magnetic field. So, typically this is like a 3 Tesla kind of field. So, I apply very large magnetic field, then I force all the magnetization to point along this direction. Then once I remove the magnetic field, now I still have a north and south pole. Okay. So, this step is important. So, you need to apply a very strong magnetic field, only then you can create a north pole and south pole and make it a permanent magnet. So, what happens when you prepare a piece of neodymium iron boron piece? Okay. So, in this piece you notice that there are tiny regions where magnetization are pointing in different direction. Okay. So, because the magnetization is pointing in different direction, you do not have a north pole or south pole, but once you apply a very strong magnetic field and even after you remove, the magnetization is retained in this direction, then you have a north pole and the south pole. So, now you have a permanent magnet. So, why does a freshly prepared piece of neodymium iron boron magnet have magnetization in random direction? What causes this randomness in the magnetization direction of this material? And that is what we are going to learn now. Okay. So, that brings us to this concept of magnetic domains. So, when you prepare a fresh piece of magnetic material, not all the magnetization is pointing in the same direction, but you will see some regions where the magnetization is pointing in one direction. So, if I zoom in this particular region, I will notice that the magnetization of the neighboring atoms are pointing in the same direction. So, if I zoom this one, the magnetization are pointing in the same direction within this microscopic region. Okay, so, within this microscopic region, the neighboring atoms have parallel magnetization, which means it is ferromagnetic. But on a whole, the system divides into many small regions with random magnetization direction. Okay. So, this property is called magnetic domains. Okay. So, domains are the tiny regions in a magnet, where within a domain the neighboring moments are parallel to each other, but within the bulk of a material you have the system pointing magnetization in different direction. So, this concept is called domain. So, you can call each of these region as a domain. So, this is a magnetic domain, this is a magnetic domain, this is a magnetic domain, and so on. Okay. So, there are many magnetic domains inside a magnetic material, especially when you have not subjected a magnetic material into a magnetized state. So, a freshly prepared material like the neodymium iron boron, which I prepared, has many domains. Okay. So, what causes these magnetic domains? Again, let me go back to, let me create a fresh page. Yeah, create a new slide. Yeah, I can use the 104.
This one.
Yeah, I can use that.
Add here just
Hmm?
just
No, it's okay. If 104 is fresh, that's fine. Okay, so let me ask you a hypothetical question. Let us say I have two magnets, the two magnets, both of them have north pole up. I try to bring them close to each other, what will happen? Huh? They will repel. Okay. What else can happen? I try to bring too close and I am not holding it tight. They can rotate, right? They can rotate and probably they will form so why this happens? Pardon? Yeah, so it's a energy minimization. Okay. So here when you have two north poles, two south poles next to each other, the energy is high. This one is state of low energy. What is the name for this energy? So, this energy is called the magnetostatic energy. Okay. So, magnetostatic energy is minimum when you have two unlike poles next to each other. Okay. And when you have two like poles next to each other, the magnetostatic energy is high. So, when you bring two magnets, they flip into this direction to minimize the energy. Okay, let us say I try to prepare a piece of neodymium iron boron. Okay, I have formed powders. So, I bring all the powders close to each other. So, each tiny piece of iron has certain magnetic moment. Okay. So, these are the atomic moments of the neighboring ion atoms. So, let us say I keep doing this along the 3 dimension. So, what happens? So, when you look at this one, this is like trying to keep 2 north poles next to each other, 2 south poles next to each other, right. So, I cannot keep piling the neighboring atoms to be parallel to each other, because when I keep doing that, I am increasing the magnetostatic energy of the system. Okay. So, the system will tend to minimize the energy. Then only way to minimize the energy is to bring some randomness or to form this kind of pattern. Okay. So, if they flip, for example, in the case of real magnets, they can flip and form this to minimize energy. So, in the case of a system like this, again they can flip, for example. In some cases we have this kind of flip. So, now you have one domain, then we have another domain and so on. Okay. So, formation of domain helps to minimize magnetostatic energy. Okay. So, here I draw 2 domains with some space intentionally. Why? Why didn't I draw like this? Yeah. But why I didn't draw? Pardon? Yeah, why? So, why I kept some distance here? Pardon? Some boundary is there. Yeah. Why that boundary happens? Pardon? Yeah, but why the boundary cannot be sharp?
So, abrupt boundary cost high energy.
Yeah. Okay. Due to some concept that we learned earlier. What is that? Yeah. So, okay. So, we learned that the Heisenberg interaction states that the neighboring spins have to be parallel. Okay. So, this is S1, S2 cos theta, theta has to be 0, right. So, if you go from 0 to 180 abruptly, then the energy is going to be very high. Okay. So, because of that reason, the spins do not change abruptly from one direction to the other direction, but they will change gradually like this. Okay. So, this boundary or this region where this transition happens is called a domain wall. So, we have 2 domains and we have a domain wall in between, and the domain wall ensures that we do not violate this. Okay. We do not increase this energy drastically. Okay. So, when you go slowly from 0 degree to some angle gradually, so the angle between these 2 spins will be for example, let us say this is like 15 degree, this is another 15 degree and so on. Okay. So, the angle theta never goes from 0 to 180 degree, but it may go from 0 to 10 degree or 15 degree depending on something that we will learn later. Okay. Okay, so here I am just visually showing whatever we discussed. So, when we try to put many atoms with spin pointing in the same direction, we are increasing the magnetostatic energy, and on the other hand, if the system forms domains, then the magnetostatic energy is minimized. Okay. So, I try to put many neodymium iron boron atoms together. So, magnetostatic energy gets increased, but the system forms many domains and minimizes the magnetostatic energy. Okay, so, this picture shows what we discussed earlier. So, we have one domain where all the spins are up, we have another domain, all the spins are down. So, in between we have a gradual change of magnetization from up to down direction, and this is called domain wall. So, there are, I mean, in perpendicular system there are like two different types of walls. One is called Neal wall, another is called block wall. So, in Neal wall, the let us say this is up spin, then this region has down spin, the magnetization goes this way. Okay. So, if you look at the, how do you remember? So, quite, I mean, when I was young, I always have difficulty to remember which one is Neal wall, which one is block wall. In the case of block wall, the magnetization goes this way, it comes towards you, then comes back down like this. Okay. Whereas, in the case of Neal wall, it just goes this way and this. Okay. So, I always had difficulty in remembering, then I came up with the mnemonics. Okay. So, when you kneel down, what you do? You are bending something like this, right. So, if you look at this one, you can see that this pen is actually kneeling down. Okay. So, remember this mnemonics to remember how the Neal wall looks like. Okay. So, these are two types of domain wall in perpendicular systems. Okay. The next question is whether a system will always form domains or not. Okay. So, I gave you the example of a neodymium and boron magnet, and I told you that here will form domains. Okay. There are also some systems where we may not form domains. Okay. Especially when I talk about recording media, the hard disk recording media. We do not form domains, no domains. So, when I prepare a recording media film, that film does not form domain. Okay. This might look surprising to you, because if you have studied about domain, you would always think that all systems will form domains, but that is not the case. Okay. There are some cases where the systems may not form domains. Okay. So, what determines whether the systems will form domain or they will not form domain depends on the competition between two energies. Okay. So, to explain the two energies, let me go back to the white screen. So, when you form a domain wall, or when the system forms domains and domain walls, the system reduces magnetostatic energy okay. So, this we have already learnt. Okay. So, it is like having a magnet flipped and attracted to each other. So, this we already learnt, but the formation of domain wall actually increases something called domain wall energy. This we have learnt. Okay, I haven't taught you what is domain wall energy, where does it come from. Okay, so, this domain wall energy comes from two aspects. One is the anisotropy, so anisotropy energy. The other contribution is coming from exchange energy. Okay, so, when you form a domain wall, there is an energy associated with formation of domain wall. Okay. So, there is an increase in the energy of the system. So, the more domain walls, then more energy. Okay. So, as you add more and more domain walls, the system's energy also increases. Okay. So, this domain wall energy comes from two factors, one is exchange energy, another is anisotropy energy. So, what is this exchange energy? Where does it come from? Okay, let us go back to the domain wall. So, let us say we have spins like this, here we have spins like this. So, within the domain wall we learned that the spins have certain angle. Okay. So, if you look at these two spins, theta is 0, Heisenberg exchange energy is the lowest, but if you look at these two spins, theta is non-zero. Okay. Even though the spins are at certain angle, this tilt actually increases the exchange energy. Okay. So, all these spins at the domain wall, they are not at theta 0 angle, they are at non-zero angle. Okay. So, because of this there is a energy. So, that energy is called exchange energy, increase in exchange energy. Okay. Secondly, where does this come from? Anisotropy energy. Let us say this is a perpendicular film, okay, a film with a perpendicular anisotropy. So, let us say this is your substrate and this is the film you prepared, it has a easy direction in the perpendicular direction. Okay, so, we know that the energy is minimum when the spins are pointing in the easy direction. So, if the spins are pointing away from the easy direction, then there is going to be some energy. So, you look at all these spins. So, these are okay, these are in the easy direction. So, there is no energy contribution from these spins, but all the spins in the domain wall region, they are not in the easy direction. So, this is deviated from the easy direction by certain angle, this is deviated even more further. So, this increases energy a little bit, this increases energy too much, and this increases the energy the most, and so on. Okay. So, because the spins are not aligned along the easy direction, the anisotropy energy also increases. So, when you form domain wall, when you form many domains, the domain walls also need some energy, increase the energy. Okay. So, exchange energy increases, anisotropy energy increases. Okay, so you can see that two cases, one is domain wall formation reduces magnetic energy, but domain wall formation increases the domain wall energy. Okay. So, finally, whether the system will form domains or not depends on the competition between these two. Okay. Suppose you have a system, and in that system if the formation of domains reduces the magnetostatic energy drastically compared to this one, then the system will form domains. Okay, suppose by forming domains you will increase the domain wall energy more than the reduction that you can gain from here, then the system won't form domains. Okay. So, that is what is shown in this picture. So, here I am plotting the energy, the energy from magnetostatic energy is given by this red line. It goes as L power 3, whereas the formation of domain wall has a L square dependence. Okay, so here you can imagine a cube, for example. Okay. So, if this L is very large, okay, then we are in this region. Okay, for large L, you are in this region. So, that means the magnetostatic energy is much larger than the domain wall energy. So, here we will have formation of domains. On the other hand, if the L is small, below a certain critical size, now the domain wall energy is more than the magnetostatic energy. Okay. So, in this case, no domains will be formed. Okay, I hope it is clear. Any doubts here? Is it easy to understand or difficult? Okay, let me show you some more slides. Okay, let us say you prepare particles. Okay, let us say you do some chemical process and you prepare nanoparticles. Okay, so, these nanoparticles have certain diameter. So, if these particles are very huge, okay, if these particles are very huge, so particle diameter is large, then you are in this region where magnetostatic energy will be is more than the energy needed to form domains and domain walls. Okay. So, in that case, this particle will not have single domain, it will have many domains. Okay. So, it will form multi domains. So, in your chemical synthesis you have lots of such particles all the particles are above certain critical dimension. So, magnetostatic energy is more than the domain wall energy. So, all these tiny particles that you have created will have multi domains. On the other hand, you have let us say another recipe where you can prepare particles with a very small dimension. So, now we are in this range. So, in this case the magnetostatic energy will not be very high. Actually, it will be lower than the energy needed if we need to form domain walls. Okay, suppose the system forms domain wall, the energy from domain wall formation will be very high. Okay, so, in this case the system will just do not bother, it will not form any domain, it will exist in a single domain state. So, when you say SD, so it means single domain. Okay. So, when the particle size is very small, the system does not form domains, but when the particle size is very large. So, you can imagine, right. So, if you have very small particles, let us say you may have 1000 spins parallel to each other. Let us say here you have 1000 spins parallel to each other, and if the particle is very very large, maybe you have like 100,000 spins parallel to each other. Okay, so, you can imagine, right. So, this will have large magnetostatic energy. So, it is better they split into domains and minimize the magnetostatic energy. Okay, so, whether the system forms domains or not depends on the competition between these two energy. For large particle sizes, magnetostatic energy is large. So, minimizing magnetostatic energy by forming multi domains is preferred, but for small particle sizes magnetostatic energy is not very high, it is low. So, it is not wise to form domains. So, the system will not form domain, it will be in a single domain state. Okay, let me show some example. So, in this picture you see tiny cylinders. Okay, from side it will look like this, but they are like this. Okay, we have tiny cylinders fabricated by lithography. The diameter of the cylinders is shown here. So, in the first case the diameter of the cylinder is 5 micrometer, second case is 500 nanometer, 200 nanometer, 50 nanometer and so on. Okay. So, we have 4 different cases with a different diameter. So, in this graph, so somewhere here, somewhere here, somewhere here, something like this. Okay. Maybe the 50 nanometer is here, 200 is here, okay, somewhere. So, you look at the 5 micrometer disc. So, you see the brown and say beige color, you see 2 colors. Basically, the 2 colors means in one brown maybe the magnetization is all up, the beige region magnetization is pointing down. Okay. So, you are looking at the domains which are either pointing up or pointing down, and you can see a lot of small lines. Okay. So, that means this system is in the multi domain state. Okay. multi-domain state. Now, we look at another cylinder, all have same thickness, this T is the same, thickness is the same, only the diameter is different. So, now you look at the 500 nanometer diameter region. So, you see here brown, beige color. So, this is one domain pointing up, this is another domain pointing down. So, here you have two domains. In this disk you can see three domains, brown, beige, brown. Here again you see three domains. So, basically 500 nanometer also domains have formed. So, it is still in the multi-domain state. So, when you go to 200, some disks have like two domains, right. So, one brown, one beige, here again like one brown, one beige. Okay. So, this is somewhere here. Okay. Some of these particles form domain, some do not form domain. Okay. But once you go to 50 nanometer, you take all these small regions, either they are fully white or fully brown, right. So, none of them have any domains like this. So, here you see like Pepsi kind of pattern you can see, but here you do not see. Here all of them are either brown or black. That means, those small disks are in the single domain state. Okay. So, this is the clear evidence that the formation of domains depend on certain critical diameter. So, if you are above that critical diameter, the magnetostatic energy is high. So, the system forms domains, and if you are below this critical size, magnetostatic energy is not that high. If you form domain, you are going to increase the domain wall energy. So, the systems do not form domains, they exist in a single domain state. Yes. Pardon? Okay, what is super paramagnetic? Okay, this is actually super paramagnetic. Okay, let me go back to the white screen. Okay, so now you are clear with these concepts, right? So, what is paramagnetic? We learned this yesterday. What is paramagnetic? What happens to the neighboring spins? Neighboring spins are randomly oriented, then they are also fluctuating as a function of time. Okay. So, your neighboring spins are randomly oriented and also they fluctuate as a function of time. So, at another time they are random again. Okay. So, this we know, we already learned yesterday. So, super paramagnetic refers to a situation that, let us say you have a ferromagnetic cylinder. Okay, you have a ferromagnetic cylinder. So, inside this cylinder you have many spins, right. So, it is a ferromagnetic material. It is a ferromagnetic material the neighboring spins are parallel to each other, but this particle is too small. Let us say this particle has a very low volume. Okay, either because the diameter is too small or thickness is small, for some reason these particles have very low volume. Then what happens is, I mean, when you have a ferromagnetic particles, the energy that keeps the magnetization in a certain direction depends on KUV, where V is the volume of the particle and Ku is the anisotropy constant of the material. Okay, so, if you multiply the anisotropy constant of the material with the volume of the particle that you have prepared, then you have this term. This is called anisotropy energy. Okay, so, this energy is the one that keeps the magnetization fixed in one particular direction. So, we learnt about permanent magnets, right. So, yesterday there was one question, why the permanent magnets retain the north pole and south pole. That is because those materials have a very large anisotropy constant. So, there is a large anisotropy energy. So, this anisotropy energy is the one that determines whether a material is hard or soft. Okay. Now, let us come back to this particular case. So, you have a particle with a very low volume. So, even if this particle has a reasonably high anisotropy constant, because the volume is small, you can say the KUV is low. Okay, so, there is one energy, anisotropy energy, that tries to keep the magnetization in a particular direction, but at room temperature, let us say 300 Kelvin, we have the thermal energy, which is basically Boltzmann constant multiplied by room temperature. So, there is a thermal energy. Okay. This thermal energy will compete with the anisotropy energy. Okay, so, in the case of paramagnetic materials, thermal energy is the one that makes the magnetization of the individual atoms to fluctuate randomly. Okay. So, similar thing can happen here. So, when this is low and compared, I mean, when these two values get closer to each other, the thermal energy may cause the magnetization of this particle to fluctuate randomly. Let us say this is the magnetization of this particle. So, I observe at time t1 magnetization is like this, at time t2 maybe magnetization is like this, time t3 magnetization is somewhere like this. Okay. So, this magnetization keeps fluctuating as a function of time, because the thermal energy starts competing with this anisotropy energy. Okay. So, here when I draw this arrow, I am talking about magnetization of this particle. Okay. But if I zoom this out, the neighboring spins are still parallel to each other. Okay. So, at one point of time, all these spins are like this. Okay. At time t2, all the spins are this. Okay. At time t3 all the spins are like this. So, what it means? The system is still ferromagnetic, okay. The neighboring spins are parallel. So, your particle is still ferromagnetic, but the particle magnetization is behaving fluctuating, okay. Particle magnetization is fluctuating as a function of time, like the atomic magnetic moments fluctuate in a paramagnetic material. Okay. So, that phenomenon is called super paramagnetism. So, the term paramagnetism basically refers to this time varying magnetic moment fluctuation. Okay, but here it is still a ferromagnet, okay, because neighboring spins are parallel, but their magnetization fluctuate. The magnetization fluctuates as a function of time due to this thermal energy competing with anisotropy energy. Okay. So, when you are in the super paramagnetic region, the particle will not have coercivity, okay, because they are fluctuating as a function of time. The hysteresis loop will vanish. So, normal case, let us say you measure the hysteresis loop here, you will have coercivity like this, but if the particle size is small, too small, then the hysteresis loop will be, I mean there is no hysteresis loop, particle will be like this. Okay, you can see the particle, super paramagnetic particle still have a large MS. They have a large MS, but they have 0 remanent magnetization and coercivity is 0. Okay, so, this is a huge difference between paramagnetism and super paramagnetism. Paramagnetism MS is almost 0, right, but super paramagnetic material will have a large MS because it is ferromagnetic. Only thing is it does not have a remanent magnetization or coercivity. So, this happens when you make the particles too small, okay, below certain dimension, the particles will be in super paramagnetic limit. Okay, let us do some questions. Okay, majority of you are wrong. Okay, so domains are formed only when there is a minimization of total energy. So, I told you 2 cases, right. So, if you have big particles, then when you form domain, you minimize the total energy, because so basically the answer 3 is the correct answer. So, you also have another case, right, single domain you are not forming domains, because you are increasing the domain wall energy. So, domains are formed only when there is a decrease in the overall energy of the system. That is why I told you, I mean not all time we form domains, right. Okay, majority of you are right. So, formation of domain walls increases the exchange coupling energy, because your neighboring spins are not parallel, they have certain angle, and because theta is not 0, we have some increase in the exchange coupling energy. So, this is the correct answer. Okay, most of you are right. So, if the nanostructures are below a certain critical dimension, they do not form multi domains, this is correct. They are single domains, correct, and they may be even super paramagnetic. If they are too small, they may be even super paramagnetic. So, all of the above is the correct answer. Okay, so now we are on the last topic of magnetism. Okay, so before I start this one, let me ask you a question. Let us say I have a piece of magnetic material. So, let us say this is iron or some magnetic material. Okay. Then I have a magnet. Okay. So, let us say this is north pole of the magnet. I bring this close to the magnetic material. Okay, then there are a few possibilities. Okay, now I am drawing the cross section. Okay, you are looking from this side. Okay, I bring magnetic material. So, you know that this material will be magnetized. Okay. So, this is scenario 1. Only the region directly below the magnets get magnetized. With the second possibility is like, even though my magnet is only this small, this whole region from here to here get magnetized by this small magnet. Okay. So, now this whole region is north pole up, south pole down. Okay. So, here this is the influence of my magnet, here this is the influenced region of my magnet. Okay. So, when I bring magnet next to a magnetic material, which scenario will happen? 1 or 2 or maybe either. Okay. So, how many of you are thinking that 1 will happen? Raise hands. No one? Okay, 1, 2, 3, okay, 3, 4 hands for this one. How many of you think that 2 will happen? Nobody? So, I bring a magnet, a wide region gets magnetized. How many of you think 2 will happen? No one? Okay, 0. How many of you think that either of this will happen? 1, 2, 3. So, 23 of you have no opinion. Nota. Okay, so, when you bring a magnet next to a magnetic material, I mean this question, right, nobody teaches in magnetism. So, many of you would have studied magnetism, nobody discusses this one. Okay. And whenever I even interview postdocs for postdoc position, I ask this question, they do not know. Okay. But this is very important aspect. As a magnetism trained person, you should know this. Okay. So, when you bring a magnet next to a magnetic material, this can happen, this can also happen. Okay. Either can happen. So, it depends on the state of your magnetic material. Okay, so, we learnt about single domains. So, in some cases we learned that the system will have no domains, all the tiny particles will be in single domain state, and we learned that in some system we will have multi domain states. So, depending on whether you prepared a system of single domain particles or whether you have prepared a system of multi domain particles, either can happen. Okay. So, in the case of single domain particle, this one will happen, okay, this phenomenon where only the region directly below the magnet will be influenced by the magnetic field. whereas if you have prepared a multi-domain system, even you bring a magnet, a large region even beyond the influence of magnet will be affected. Okay. So, this aspect of how a magnetic material responds to the applied magnetic field is called magnetization reversal mechanism. Okay. So, how a magnetic material responds to a magnetic field is called magnetization reversal mechanism. So, it can happen through many possible ways. So, one mechanism is called domain wall motion. Okay. So, this is one type of reversal mechanism. Then another type of reversal mechanism is called coherent rotation, which is proposed by these two scientists, Stoner-Wohlforth. So, it is also called Stoner-Wohlforth reversal mechanism. Then there are also some other more complex reversal mechanisms, but let us just stick to these two reversal mechanisms today. One is domain wall motion, the second one is coherent rotation. So, as this slide implies, coherent rotation happens when you have a system of single domains, and when you have a system of multi domains, domain wall motion is the dominant reversal mechanism. Okay, you do not need to read through the text. Let us say you have a system where you have many domains, and now you apply a magnetic field along this direction. The region where the magnetization is pointing in the same direction as the magnetic field expands. So, you can see that this region has expanded. So, initially the domain wall was here. Okay, you can see that this domain wall has moved. Okay. So, the domains which are in the same direction as the applied magnetic field, they expand. Okay. So, this kind of reversal mechanism is called domain wall motion. Okay. So, you can observe in this video. So, here let us say black means the magnetization is going into the board, gray means magnetization is pointing towards you. Okay. So, this video is taken using curve microscopy in my lab. So, we can observe the domains, domain wall motion and so on. Okay. So, you can see when we apply certain magnetic field, these domains expand. Okay. So, the black domain expand. So, this is the domain wall. Okay, at this point of time, this is the domain wall. You can see the domain wall expand, and at this point of time the domain wall is here, and you can see the domain wall moves, right. So, this is the domain wall motion reversal mechanism. So, normally when you make, let us say you are making thin films, let us say you are depositing thin films, right, without any special technique. Let us say you deposit a piece of cobalt film or any film without some special technique. So, this film usually forms the case where you have multi domains. It's quite common to form magnetic material into multi domain state. So, if you want to form single domain states, you have to make the particles too small, or you have to employ some techniques to achieve single domains, but the default case is that when you deposit a magnetic film or prepare some magnetic material, it always form multi domains. Okay. So, when you have such films, the reversal mechanism is always domain wall motion. Okay. So, this is what I meant. The reversal mechanism depends on the state of your film. So, if your film or sample has multi domain state, then you will have this domain wall motion reversal mechanism. Okay, so, when you have a film, let us say you have a film so, within this film, due to the composition inhomogeneity or something like that, you may find some regions where the energy is different, energy landscape is different compared to the rest of the region. So, for example, this region A, the energy is low, region D, the energy is low. So, when a material is like this, usually when the domain wall comes here, it will get stuck. Okay. If you apply some more energy, the domain wall will be released from here, and maybe it will go here and get stuck. Okay. So, some energy minima in the system will stop domain walls, and we call them as spinning sites. So, these are common features of domain wall motion. And if you have studied Barkhausen noise, this Barkhausen noise comes because the domain walls are getting stuck at many pinning sites and they get released and so on. Okay. Now, let us come to the second point. Second point is another type of reversal mechanism called coherent rotation. Okay. So, this happens when you have a system of single domain particles, which means your particle size is small. So, within that particle you do not have domains, it is a single domain. Okay. So, what happens to the magnetization of the particle when you subject them to magnetic field was studied theoretically by these two scientists, Stoner Wohlforth, and they propose how they will, these particles will reverse their magnetization when they are subjected to a magnetic field, and this model is called Stoner Wohlforth reversal model. So, here they undergo coherent rotation, which means when you apply magnetic field, let us say initially all the spins within this particle are parallel, pointing like this. Let us say you apply magnetic field in this direction. So, when they go from up to down, so at some point of time maybe all the spins are like this. Okay. At another point of time they may be all like this. So, you can see that they are all coherently going together from one direction to the other direction, like the synchronized swimmers they do in Olympics. So, they all behave like synchronized to each other. Okay. They go coherently from one direction to the other direction. Okay. So, this is what it means, all the spins rotate together with respect to the external magnetic field. Okay. So, according to this Stoner-Wohlforth reversal mechanism, let us just highlight the results rather than the derivation. So, if you measure the, let us say now we are taking just one particle. Okay. So, we take one imaginary particle, let us say it has the easy axis along this direction, and I apply, let us say magnetization is initially in this direction, I apply magnetic field in the opposite direction. Then this particle, initially it was like this, once I apply reverse magnetic field, it reverses to the other direction at a field called Hk. Hk is called anisotropy field. Okay. So, again now this particle is down, so I apply magnetic field in the other direction, it goes back to this state at the same field Hk, and the value of Hk according to the Stoner-Wohlforth reversal model is given by this. So, Ku is the anisotropy constant of this material. So, different materials have different anisotropy constant. So, depending on the anisotropy constant of the material and the Ms, this Hk will be different. So, some materials like iron, platinum have Hk as high as 7 Tesla. Some materials like say cobalt, platinum alloy for example, they may have 2 Tesla Hk. So, depending on the Ku and Ms, this Hk may vary. Okay. So, but the important point is that the reversal happens at this field. So, when the applied field is more than this 2 Ku over Ms, the particle will change from one direction to the other direction, that is in the easy direction. Okay. But if you apply in the hard direction, the magnetization will slowly rotate. So, initially magnetization is like this, you are applying magnetic field in the hard direction. So, the magnetization will slowly rotate at some field. So, when the field is more than Hk, the magnetization is completely pointing in the direction of your applied field. Okay, but once you remove the magnetic field, it will come back to the easy direction. Okay, this is what we learned before also. Okay, so, in the hard direction, there is no hysteresis loop. So, when you take a single particle under Stoner-Wohlforth model, there is no coercivity in the hard direction. Okay. Remanence is 0, coercivity is 0. This one is a theoretical model. Okay. Theoretically, if you take one particle, it will have 0 remanence, 0 coercivity when you measure hysteresis loop in the hard direction, but you notice the Ms is still the same. Okay. So, this, if you remember, I asked you one question whether Ms is same or not. So, Ms is the same. Okay. In the hard direction, when you apply field more than the anisotropy field, the system will go to the saturation magnetization. Okay. So, this is the easy direction, hard direction. What if you apply magnetic field along certain other angle like 30 degree, 60 degree, the hysteresis loop will look like this. Okay. So, this is one way of explaining what happens to a Stoner-Wohlforth particle when you apply magnetic field. Okay. So, let us say this particle has a easy direction along this one. So, the magnetization can point like this or like this. Okay, there are two possible states. one is magnetization pointing this direction or magnetization pointing in this direction. So, those two are the lowest energy states. Okay, so, you can see that let us say this is called energy landscape. So, you plot energy as a function of the angle between the field and magnetization, angle between the easy axis and magnetization. Okay, so, when the magnetization is parallel to the easy axis, parallel or anti-parallel, the energy is low. And as I mentioned, if the magnetization is pointing 90 degree with respect to the easy direction, energy is high. Okay, so, this is the energy landscape when there is no magnetic field. Okay, when you do not apply any magnetic field, this is the energy landscape, and this value is called energy barrier. That means, the difference between the lowest energy and the highest energy is the energy barrier, and this is what is called KUV. I already described before. When I discussed super paramagnetism, I talked about this energy barrier KUV. Okay. So, all single domain particles according to Stoner-Wohlforth model have an energy barrier EB given by this expression. So, it depends on the volume of the grain and the anisotropy constant Ku of the material. Okay, now, let us say you apply some magnetic field, you increase the magnetic field. So, when it is close to the coercivity, you can see the energy landscape has changed. This direction, this one has the lowest energy, and this is the excited state. And once you reach a field closer to the coercivity, there is no energy minima here. Okay, so, the particle cannot exist here, it has to go to the energy minimum. So, this is where it switches from magnetization pointing up to pointing down. Okay. So, when the field is more than the coercivity, basically there is no energy minima, particle will switch. Okay. So, this is the concept of Stoner-Wohlforth reversal mechanism. It is lunch time, right? Let me see whether there is anything very important. Okay, there are some questions to be asked. So, maybe let me ask those questions as a recap during tomorrow's lecture. Okay. So, we will stop here, we will go for lunch, then we will continue from where we left.